The tardigrades. In 2007, scientists exposed microscopic creatures to the vacuum of space. No oxygen, no protection, lethal radiation pouring down from the sun. When they brought them back, some were still alive. The experiment was called TARDIS, Tardigrades in Space, part of the European Space Agency's Photon M3 mission. Tiny creatures, barely half a millimeter long, sat on the outer hull of the spacecraft. For 10 days, they faced the same vacuum, ultraviolet light, and cosmic rays that would kill any known animal. These were tardigrades, water bears, small, soft-bodied organisms known for their toughness on Earth. But nothing prepared researchers for what happened next. When the capsule returned, the samples looked dead. Then scientists added a drop of water. Within hours, some tardigrades began to move again. They stretched their limbs. They woke up. Even more astonishing, some went on to reproduce normally. Their DNA had suffered radiation damage, but their cells repaired it almost completely, like they had a built-in reset button that could restore life after the impossible. Astrobiologists were floored. If these tiny animals could endure the vacuum of space, could life survive on a meteorite traveling between planets? Could it hitch a ride across the solar system, or even farther? The idea wasn't new, but now it had evidence. Panspermia, the possibility that life might spread through space itself, suddenly felt less like theory and more like nature's backup plan. Of course, not every tardigrade made it. Most that faced direct, full-spectrum radiation didn't survive, but enough did to rewrite what resilience means. For scientists at NASA and ESA, the lesson was clear. Biology adapts in ways we still barely understand. The agencies started studying tardigrade DNA to find the molecular secrets behind their near immortality, mechanisms that could one day protect human cells from radiation or freezing. The humble water bear had done what humans could not. It had looked into the face of space and survived. If a creature smaller than a grain of salt can survive the void itself, what might that say about life's true limits, or where it came from in the first place? DNA mutations. In orbit, bacteria don't behave the way they do on Earth. They multiply faster, they mutate differently, and sometimes they become harder to kill. NASA learned this the hard way. On the International Space Station, researchers ran experiments, Microbial Tracking 1 and Gene Lab, to study how space changes living cells. What they found was unsettling. When bacteria like Salmonella or E. coli grew in orbit, they didn't just survive, they adapted. Their genes switched on new responses, as if rewriting their own rulebook to match the strange physics of weightlessness. On Earth, fluid movement and heat distribution help cells grow in balance. But in microgravity, everything changes. Nutrients don't mix, waste doesn't settle, stress builds quietly inside each cell. And under that stress, something remarkable happens. Survival genes awaken. In one mission aboard the space shuttle, Salmonella typhimurium came back stronger than before. Tests showed it was more virulent, more capable of causing disease than its Earth-grown counterparts. When scientists sequenced the DNA, they found changes in genes controlling stress response and cell membranes. The bacteria had essentially evolved under pressure, not over centuries, but within days. For NASA, this was a wake-up call. Space doesn't just challenge humans, it challenges every microbe we bring with us. And if the simplest organisms can change this quickly, what might that mean for the future of long missions, to Mars or beyond? Follow-up studies confirmed the pattern across multiple species. Microgravity wasn't just a strange environment, it was an evolutionary accelerator. Cells adapted to cosmic radiation, low shear forces, and isolation by altering their DNA itself. The same pressures that weaken human muscles seem to push microorganisms toward strength. That duality fascinated researchers, because studying how microbes mutate in space could one day help us protect our own DNA, or even slow aging and disease on Earth. In a world without gravity, life finds new ways to survive. Even the smallest organisms rewrite the rules to endure the infinite. If microbes can evolve this fast among the stars, how will we change when we start living there too? Water from urine. In orbit, every drop counts. The air you exhale becomes tomorrow's breath. The moisture from your skin, the vapor from your lungs, even your urine, is reclaimed, purified, and reused. When NASA introduced the water recovery system in 2009, it wasn't just an engineering upgrade. It was a step toward complete self-sufficiency. The goal, a closed-loop ecosystem where nothing is wasted. Inside the ISS, humidity is condensed from the air, filtered through multiple membranes, distilled under low pressure, and treated with catalytic oxidation. The result? Water so pure it often tests cleaner than tap water on Earth. But getting there wasn't easy. Early versions failed dramatically. Filters froze, pumps jammed, microbes bloomed in unexpected corners. NASA engineers spent months refining each component until recovery efficiency reached over 93%. Then came the human challenge, convincing astronauts to drink it. Commander Chris Hadfield once put it simply, "Yesterday's coffee becomes tomorrow's coffee." Today, that system keeps every crew alive, recycling sweat, breath, and waste into a continuous supply of clean water. What started as a survival mechanism has become a lesson in sustainability, one that echoes back to Earth. Because in space, nothing is disposable. And on a planet of finite resources, maybe it shouldn't be here either. The cool flames. In orbit, fire behaves like nothing on Earth, no smoke or even a flicker. A small blue sphere hovers in mid-air, burning without heat and without light. Inside the International Space Station, astronauts watch in silence. It shouldn't exist, yet there it is, a perfect glowing sphere suspended in zero gravity. The year was 2012. NASA's Combustion Integrated Rack ran experiments on how fuel burns in space. Astronauts ignited tiny droplets to study how flames spread and die in microgravity. But one day something strange happened. After the bright yellow flame vanished, sensors showed the fuel wasn't done burning. Something invisible was still consuming it. A second fire, unseen, cool, and slow. They called it the cool flame. On Earth, flames rise because hot air moves upward. But in space, there's no up, no down, no convection to carry heat away. Here, fire takes on a completely different form. The cool flame burned at only 800 degrees Fahrenheit, far lower than any normal flame. It gave off almost no light. It just existed. A quiet chemical dance, steady and efficient, as if feeding on its own logic rather than heat. Scientists were stunned. This kind of flame had never been seen before. It didn't follow the same chemical pathways as regular combustion. It was, in a sense, a new kind of fire, one that could only exist in the weightless void. The discovery raised unexpected questions. Could this teach us to burn fuel more cleanly on Earth? Could it lead to engines that waste less energy or spacecraft that handle fire more safely? Over the next few years, NASA ran more tests. The results stayed consistent. The cool flames lasted for minutes, perfectly stable, consuming nearly every drop of fuel. They were silent, efficient, and strangely beautiful. In a place where fire should be chaos, space revealed its quietest form. A flame that whispered instead of roared. It reminded scientists of something profound, that the universe doesn't just destroy, sometimes it refines. And if space can give birth to a fire that burns without light, what other hidden forms of matter and energy are waiting out there? The Lost Tool Bag, November 2008. Two astronauts work outside the International Space Station, repairing a solar array. Then it happens. A simple slip. A white tool bag drifts out of reach and into open space. Within minutes, it becomes one of the brightest man-made objects orbiting Earth, visible to anyone with a telescope and clear skies. During the STS-126 mission, Heide Marie Stefanishin Piper was cleaning a rotary joint when her gloves, slick with grease, lost grip on her toolkit. She reached for it instinctively, but in microgravity, momentum has no mercy. The bag floated away, spinning slowly, sunlight glinting off its surface like a mirror. NASA's cameras caught every second. Mission Control watched in silence as it drifted beyond reach. Inside that bag sat $100,000 worth of specialized tools. For a few moments, engineers debated recovery, but one wrong move could endanger the crew. They had to let it go. The tool bag got logged as an official orbital object, 2008-062b, a lost satchel turned satellite. Amateur astronomers around the world started tracking it, posting sighting times online. Night after night, a faint moving light crossed the sky, the trace of a human mistake, looping above the planet every 90 minutes. For 3 months it stayed in orbit, slowly falling as the atmosphere dragged it down. Then, in early 2009, it re-entered over the Indian Ocean and burned to dust. NASA called it a minor loss, but the image stayed with them, a bag of tools gliding across the stars, born from one brief human lapse. Inside NASA, that moment forced changes. If one misplaced object could create a temporary satellite, what happens when hundreds accumulate? Engineers warned of a cascade effect, collisions multiplying debris and endangering future missions. New safety protocols followed, stronger tethers, double-checked restraints, redesigned tool belts. Even in space, human error leaves a trail. The Earthrise, Christmas Eve 1968. 3 men circled the moon, 240,000 miles from home. As their spacecraft drifts into sunlight, something rises beyond the grey horizon. A small, glowing sphere, blue, white, alive. It is Earth. For the first time in history, humanity sees its own world hanging in darkness. Apollo 8's mission was meant to be a technical rehearsal, a test of engines, navigation, and courage before the first lunar landing. But what the crew found wasn't just the moon, it was perspective. As William Anders adjusted his camera, he noticed a curve of color emerging over the barren surface. He raised his lens and captured Earthrise. The image would become one of the most influential photographs ever taken. That moment wasn't in any flight plan, no checklist called for wonder. Yet it became the mission's defining achievement, not a step on another world, but a glance back at our own. Later that night, as the astronauts broadcast live to millions back on Earth, they read from the book of Genesis. Their words echoed across a planet divided by war, protest, and grief. And in that broadcast, something quiet happened. The world paused and listened. When Earthrise was released, it spread faster than any political message or scientific paper. Scientists marveled at its technical precision. Artists saw poetry. Philosophers called it the beginning of a new consciousness. And for environmentalists, it became a symbol, proof of our planet's fragility, a single oasis in an endless dark. NASA had set out to explore another world. Instead, it handed humanity a mirror. For the first time, every border, every city, every living thing existed within one delicate frame. Earthrise reminded us that exploration isn't just about leaving home, it's about seeing it clearly for the first time. The Earth's neon halo. From orbit, the night side of Earth isn't darkness at all. A soft ribbon of green and orange light wraps the planet, glowing where the atmosphere fades into space. It's called airglow, and it's the planet's quiet pulse made visible. The phenomenon begins when sunlight excites atoms and molecules high above the surface. As they relax, they release energy as faint light, photons that form a global halo, circling the Earth every night. Early astronauts first mistook it for dawn on the horizon, but scientists soon realized it's constant, even when the sun is far below. Unlike the aurora, airglow isn't a rare event. It shimmers everywhere, all the time, shaped by solar storms, shifting seasons, and even ocean-borne gravity waves that ripple upward through the air. By studying it, researchers can track how energy flows from the surface to the edge of space, linking weather and space weather into one continuous system. To the astronauts who witness it, airglow looks like a living boundary, a reminder that Earth is never still, even in silence. Lightning and sprites seen from orbit. From the cupola of the ISS, the world below looks calm until night falls. Far beneath, thunderstorms flare like electric oceans. And then, in a blink, a burst of red light shoots upward, not down. A pillar of plasma, reaching toward space itself. For decades, pilots swore they'd seen it, flashes above the clouds, gone before the eye could focus. Scientists dismissed them as tricks of the atmosphere. Then, in the 1990s, the space shuttle's cameras captured proof. Red sprites, blue jets, and elves. Enormous electrical discharges firing from the tops of storms into the upper atmosphere. Seen from orbit, they look otherworldly. Tendrils of light stretching 90 kilometers high, brushing the edge of space. Their discovery revealed that lightning doesn't just strike Earth. It connects Earth to the sky itself. NASA's Atmosphere-Space Interactions Monitor, mounted on the ISS, now tracks these events in ultraviolet and X-ray wavelengths. Each flash helps scientists map how thunderstorms charge the ionosphere, shape weather, and even disturb radio and GPS signals. Every time the station passes over a storm, astronauts still pause to watch. Because even after thousands of years of living beneath the sky, Earth keeps showing us it's still full of unseen wonders. The Floating Glove, June 1965. Two astronauts orbit the Earth during America's first spacewalk, and something drifts past their window, a pale white glove, turning slowly in the dark. Nobody mentions it on the radio. Nobody brings it back inside. But for weeks afterward, radar stations track a strange new object circling Earth. During the Gemini 4 mission, Ed White made history floating outside his capsule, tethered by a thin umbilical cord, while Jim McDivitt watched from inside. Later, as they passed over the Atlantic, McDivitt spotted something odd through the small window, a white, glove-shaped object tumbling beside them. He radioed it in, calling it unidentified debris. Ground control dismissed it at first, probably one of the gloves lost during the spacewalk. But the timing didn't add up. No glove floated away immediately after White came back inside. This one appeared several orbits later. Soon, radar stations picked up a tiny metallic echo following Gemini 4's path. They called it the Ghost Satellite. Even newspapers ran stories about it. For a few days, a lost astronaut's glove became one of the strangest artificial satellites in history. The accident revealed something more serious, that even a small object once freed in orbit stays up there for weeks or months, moving at 17,000 miles an hour. Invisible, but deadly. NASA later confirmed it was a sobering lesson. Every glove, bolt, or tool left behind would stay aloft until drag pulled it down in a silent streak of fire. But to the public, that drifting glove became something else, a human relic, our first accidental monument in space. Weeks later, the glove fell back into Earth's atmosphere and burned up unnoticed. But its story stuck around. It proved that space isn't empty. It remembers. And if a single glove could circle Earth for weeks, what else have we already left up there drifting unseen, writing the quiet history of our civilization above the clouds? Bone and muscle loss. In orbit, time works differently. Not on the clock, but in the body. Astronauts can age decades in a matter of months. Their bones thin. Their muscles shrink. Even the heart, the most tireless muscle of all, begins to forget how to pump. Since the earliest space stations, scientists have tracked what happens when the human body is freed from gravity's pull. Weightlessness isn't freedom, it's deprivation. Calcium leaches from bones that no longer bear weight. Muscles, idle in the absence of resistance, waste away. Even blood shifts upward, distorting pressure, vision, and balance. On Earth, gravity shapes us every second. In orbit, the absence of that constant force begins to unshape us. Studies on the ISS show astronauts can lose up to 2% of bone mass per month. Treadmills strapped with harnesses, resistance devices, high-protein diets, they slow the decline, but can't stop it. The body, built through millions of years under Earth's gravity, starts rewriting itself for survival in a world without up or down. Like every cell receives a quiet signal. The old rules no longer apply. When astronauts return, recovery is slow. Some regain full strength, others never fully do. Every mission brings back new data and new warnings. For journeys to Mars, lasting years in microgravity, the stakes grow higher. NASA's medical teams call it evolution in fast forward, a living experiment on how adaptable or fragile we really are. Because each time we leave Earth, we test not just our machines, but our biology itself. If our bodies weaken the moment we escape gravity's grip, does the cosmos reject us? Or is it quietly inviting us to evolve?